Given three massive bodies interacting gravitationally, determining their exact trajectories for all future time is a mathematical dead end. In 1890, Henri Poincaré proved that the general three-body problem admits no closed-form solution. To study gravitational physics, we have to simulate it. Computing the gravitational pull between every single particle requires evaluating n-squared interactions per frame. As particle counts grow, that exponential scaling curve quickly paralyzes even the most advanced processors. In 1986, Barnes-Hutt dropped complexity to O(n) log n by grouping distant particles into an octree hierarchy. If a cluster's radius-to-distance ratio is less than the parameter theta, the algorithm approximates that entire cluster as a single mass. While Barnes-Hutt solved the complexity problem on paper, translating that recursive tree logic into C++ code exposes a fatal architectural flaw. Developers often assume that achieving O of n log n mathematical complexity means the optimization is complete. They ignore how the compiled code actually physically interacts with silicon memory. Classical octrees are built using nodes connected by pointers. The code allocates these nodes dynamically on the heap as the tree grows. Traversing down the branches of this tree generates a completely chaotic memory access pattern. The CPU blindly follows physical memory addresses scattered randomly across RAM. Every time a pointer dereference occurs, the CPU checks its local, high-speed L1 cache for the data. Because the memory access is unpredictable, the hardware prefetcher fails to anticipate what data is needed next, risking a cache miss. An L1 cache hit resolves in about 4 clock cycles. A miss forces a full DRAM fetch, which stalls the processor pipeline for nearly 200 cycles while it waits for the data to arrive. In a million-body simulation, the working set of the pointer tree massively exceeds the capacity of both the L1 and L2 caches. The CPU is forced into a state of continuous, agonizing DRAM fetches. At this scale, algorithmic complexity no longer dictates performance. The simulation is entirely bottlenecked by memory. Mathematical elegance on paper is useless if the CPU pipeline spends its time stalled, waiting for scattered bytes to travel from RAM. The SX-FlatTree architecture eliminates this bottleneck through data-oriented design. It strips pointer indirection out of the codebase completely. The engineering challenge is mapping a three-dimensional spatial hierarchy into a single, contiguous 1D array without allocating a single tree node. The solution lies in Z-order Morton encoding, a mathematical technique that serializes three-dimensional coordinate space into a linear sequence. The algorithm takes the quantized x, y, and z coordinates of a particle and interleaves their individual bits, expanding them into a single 63-bit integer sequence. This generates a critical spatial property. Points physically close in 3D space produce similar 1D Morton index numbers. By sorting the array by this indexed, the algorithm forces spatially adjacent bodies to sit next to each other in physical memory. Morton encoding takes a chaotic, floating cloud of three-dimensional objects and orders them into a perfectly cache-aligned data structure, optimized for sequential hardware scanning. With the 1D array sorted, the code statically partitions the data into fixed, contiguous chunks of 64 to build the spatial hierarchy. At level 1, the system groups 64 particles, computing a single center of mass to form a superbody. At level 2, it aggregates 64 superbodies into a larger galaxy boundary. At level 3, it groups 64 galaxies into massive clusters. This entirely flat, three-level implicit hierarchy maps millions of bodies using only O(n) storage. Zero heap allocations are made. The spatial tree has been decoupled from traditional data structures. The hierarchy is now purely mathematical index arithmetic layered over contiguous blocks of memory. To evaluate gravitational forces, the system traverses this structure iteratively. It loops flatly down from the broad L3 clusters directly to the exact L0 stars using simple sequential array passes. Checking the distance against the opening criterion is no longer a recursive pointer jump down a tree branch. It's a predictable, flat array read. Because the access pattern is linear, hardware prefetchers detect the stride. Silicon looks ahead, proactively loading cache lines into L1 before the processor even asks. This proactive loading successfully hides the 200-cycle DRAM latency that crushes classical Barnes-Hutt implementations. By removing the pointers, the code stops fighting the underlying architecture. The silicon continuously feeds data to the computational cores, achieving maximum throughput without stalling. We can measure the exact performance yield of this flat hierarchy by running a 1,000,000 body simulation under a uniform distribution. This chart compares the work reduction of the 3-level hierarchy against a naive algorithm, achieving a 124x work reduction. Out of 10 billion theoretical pairs, 99.2% are cleanly eliminated. Of the remaining interactions, 76.6% are exact calculations at the near-field level. Because these L0 particles are perfectly Morton sorted, the CPU processes them sequentially, operating at peak memory bandwidth. The SX-FlatTree architecture computes the essential near-field physics exactly, while simultaneously and aggressively optimizing the far-field approximations to maximize hardware efficiency. This graph displays the empirical Pareto frontier, mapping the trade-off between force error and computational speedup. The data reveals a sweet spot at theta 0.5, achieving a 201x speedup with just 0.55% mean relative error. The scaling is superlinear. Shifting the opening criterion from 0.3 to 0.5 multiplies the speed by 3, while keeping physical error strictly under 1%. And these massive million-body performance metrics aren't just theoretical calculations. They were successfully generated and validated entirely on a standard consumer-grade mobile ARM processor. This final chart compares that 201x multiplier against other exact algorithms evaluated in the SX series, demonstrating the massive throughput advantage gained by flattening the data structure. Treating memory as a frictionless, abstract concept limits complex simulations. Maximum performance requires mathematical logic designed specifically for the physical realities of silicon.